Hello, hope you're doing well. Today we're going to be going into the analysis of the flip climb. Just trying to walk you through our engineering process and how we validated the design before we built it. Hopefully we can pick something up. We're not going to go into every detail, but yeah, hopefully learn something. So this is our CAD model flip climb. We're just going to go through a few components here real quick to get y'all comfortable. We're breaking it down in three primary parts. We have the superstructure.
Big part here.
The pole, which is what attaches to the tower, and the high torque assembly, which is what lets the superstructure rotate around the pole, lifting the whole robot. All right. So first, we need to go over some terms. The kind of process of structural analysis by hand is really comprised of finding what are called points of interest. So if we have, for example, this beam that we're analyzing, and we want to see when it will break, if you bend it, you kind of intuitively might know that it will crack on the top here. So what we would analyze is that point for the stresses there. So these equations that we're going to walk through are how you find the stresses at these points of interest, although you can find the stresses at any point. If we wanted to know the stress at this point here, we could, but it wouldn't be our point of failure. So first thing we're going to look at is a pure tensile pull. So if you have a sample and you apply a load along its length, the stress you get is a function of the force applied and the cross-sectional area. That's going to be force divided by area is equal to sigma. Sigma is going to be our stress value in the normal direction. That's what we call this pull. The other fundamental type of stress is what's called a shear stress. So if we have that same object and we apply a load across it, such as this, then what we're going to happen is rather than pulling it apart, it's going to slip. That is called a shear failure. The shear stress equation is the force in the shear direction divided by that same cross-sectional area is equal to shear. Okay? Next, we're going to analyze bending and torsional stresses. Bending creates a normal stress in the very top of the beam. There's a compressive stress on the bottom, but the failure mode of tearing is a one of tension. The equation for that is going to be MC over I, which is the moment in bending divided by your distance from the neutral axis, which is like the middle of your beam, multiplied by the distance from your neutral axis, divided by I, which is a property of the cross-section of your beam. For torsion, it's much the same. As you twist, you create a shear force. So you see how they're slipping past each other? That's a shear force. And that's going to be torque times your distance from the center of rotation divided by J, which is your rotational resistance to bending. So these four equations are all we're going to need to analyze the structure of the flip climb. Let's establish some failure criteria. So failure is reached when it's bent beyond its ability to transform back to its original state. So if we had this piece of metal, we bent it, we let go, it comes back, it hasn't failed. If we bend it and it stays bent, it has yielded, it has failed. For aluminum, the stress we're going to look at for bending is 40,000 pounds per square inch, right? So looking back at our normal force, that's 40,000 for every square inch of area. We can also write that as 40 KSI, or kilopounds per square inch. And that's going to be for aluminum. For steel, we're going to use the number 80,000 PSI, which is steel has a wide range of strengths. That's a very normal strength for an average mild steel. That's equivalent to 80 ksi. These are your equivalent stresses of failure. So we're going to write them as sigma prime because as you combine shear and tension in various ways, you can get amplified stress. But most materials are defined based on just a tensile test. So we define it as 80 ksi, but it may fail a combination of those. All right. So the first thing we're going to validate is our robot superstructure. So this outer structure here is the superstructure of a robot. We're starting with this because it's a little more comfortable to analyze than the pole. The forces are a little lower and the loads are simpler. As we look at this loading, we're analyzing the forces exerted from the climbing mechanism on the superstructure of the robot. There's going to be 150 pounds pure vertical in lifting from the bearing assembly or the torque assembly. Additionally, in the side direction, we're going to get a maximum load of 3,600 inch-pounds of torque. So that is the force the torque assembly exerts on the superstructure as you lift the robot through this maximum moment case here. So this is when your center of gravity is furthest away from where you're rotating around. So let's look at the superstructure analysis. Here's a front view of our robot under load. We experience 150 pounds in the vertical direction. That 150 pounds has to be resisted by this cross section of superstructure. We know that we have 4 members in that cross section. Each is a 1/16 inch wall piece of aluminum box tubing. Each one has an area of 1/8 of a square inch, resulting in a total cross section across all 4 of 0.5 square inches. Using our normal stress formula from before, we're going to take 150 pounds, divide that by 0.5 square inches, and we get 300 psi of stress. We calculate a factor of safety with that, meaning how many times that load would we need before we failed. We're going to take 40,000 pounds, divide that by 300, and we get a factor of safety of 133.3. That's good. That's good enough. We're going to target 2 for this build. 2 is a pretty tight factor of safety, but we're not life supporting. Weight matters in FRC. It'll be all right. So now we're going to look at the side loading case. In this case, looking at the side view of the robot, we are trying to resist a 3,600 inch-pound bending moment about the rung and transfer that to the rest of our robot. We're sharing that load among 4 different profiles. So we're going to take 3,600 and assuming load sharing, we find that we get 900 inch-pounds of bending torque in each member. Now, to decide which member we're going to use, we need to compare that to the strength of each individual member. So these are the bending moment failures of a specific profile that we collected in testing in a previous video. We compare the light 1x1 tubing to our target of 900 inch-pounds, and we find that it can carry 2,200 inch-pounds. So to calculate a factor of safety for that, we take 2,200 inch-pounds divided by 900, and we get 2.4 as our factor of safety. So that validates our superstructure design at the high level. Where this will get you is if you don't gusset your 1x1 well enough to support that 3,600 pounds of load. As you can see in our CAD here, we transfer that load from our torque assembly through 1x2 tubing into our 1x1s through pretty large gusset plates. These are likely overbuilt, but you do need some ability to transfer those forces. The final part of the superstructure we're going to look at is how we're supporting the torque assembly. So the torque assembly is comprised of two long beams that have a rotational member in the middle, and then those have our post. Our post, again, is driving against that at 3,600 inch-pounds. This creates a counteracting load in each beam across them of 513. So again, we want to figure out what profile will have the correct bending moment to resist that. So if we look at a side view, we find that our force of 514 pounds is reacted by two forces in the opposite direction. Those forces are going to have a magnitude of half of 514. So that's going to be 250 and 250. Those are going to create a couple, which is going to bend our beam about this distance here, right? So the unsupported length of that couple is 9 inches. We can multiply 250 by 9 to find our maximum bending force. 2,250 inch-pounds per profile. Let's compare that to the strength of the profile we used. So as we look here, we are targeting 2,200 inch-pounds with a margin of more than 2. So we're really looking for a profile that is stronger than 4,400 inch-pounds. We're gonna keep going, not strong enough. And then as we get to the vertical light 1x1, we find that it fails at 5,800 inch-pounds, which if we calculate a factor of safety on, we find a factor of safety of 2.5, meaning that these transverse elements are now validated. So if we look back to our full superstructure, we have validated the ability of the light 1x1 to hold the vertical force. We validated the ability of the light 1x1 to hold the rotational force, and we have validated the cross member's ability to resist the torque from the torque assembly without snapping.
Bang.
All right, so now we get on to the slightly more difficult structural analysis of the pole structure itself. So we're going to break the pole structure into a couple of separate parts that we're going to look at independently. So the pole is comprised of a pole, right? So there's a first pole that leads into a box tube that is then attached to a faceplate that is then attached to a finger and a nubbin, right? These are all the elements that we're going to analyze today. We're going to look at them in CAD real quick. The long pole is this element right here. The box is this element right here. And the fingers, the hook is this one right here with a little blade on it. And we have the nubbin on the other side. So this is a pretty classic example of combined loading. The entire assembly needs to resist the 150-pound robot load at the very end of the pole and the 3,600 inch-pound torque from the robot turning itself around the mechanism. So we're gonna start with the thin pole here. If we draw out its bending diagram, assuming that one end is fixed, as it approximately is with this assembly up here, we're going to apply the loads, 150 pounds and 3,600 pounds. 3,600 inch-pounds, my apologies. The point of interest that we're going to analyze is going to be on the very top of the section here. So as the pole is bent, it's going to want to crack right there on the top. Torsion is equal across the whole thing. The whole thing resists twisting equally. So we're going to just calculate for the outer surface, particularly on that top edge. All right. So we're going to use MC over I to calculate our bending normal stress. And we're going to use TC over J to calculate our torsional shear stress. To get those, we're going to need to calculate the I and J of this in particular profile. So we're going to cut to on shape real quick to get that calculation. All right. So we are looking for two numbers. We're looking for I and J. We're going to find I to be 0.325 and J, which is the polar resistance to bending, to be 0.65. Can you also give me an outer diameter of that?
Yeah.
Our pole has an outer diameter of 2 inches. Meaning that our largest distance away from the neutral axis is going to be 1 inch. So that's going to be our C value. All right, let's plug everything in. So for our bending moment, that is going to be, look at the maximum bending moment in the yellow tube in particular. So the yellow tube does not carry the same bending moment as the whole structure, because the bending moment gets larger and larger and larger as you get closer to the root. So what we're going to want is the distance from the point we're loading from to the point that the thing is resisting. We're going to take that as this face to this face. It's not exactly right, but it's going to be close enough. So that's going to be 14 inches. All right. Now we take that 14 number and we're going to multiply it by 150 to get our bending moment on the root here, which is going to be 2,100 pounds. We're going to plug that 2,100 into MC over I. So that's going to be 2,100 times 1 divided by our bending resistance, which is going to be 0.325. If we plug all those in, we're going to get 6.4 KSI. Then we're going to do the same for torsion. So our torque is 3,600 inch-pounds. Multiply that by our distance from the neutral axis, which is 1 inch, divided by 0.65, and we get 3,600 divided by 0.065 divided by 0.65, not 0.65. We get 5.5 KSI. So that's our normal, and that's our shear at that point of interest, the top one on that beam. So to find our equivalent stress state, we're going to add our normal and shear together. So normal plus shear gives us that sigma prime that we talked about earlier. So it's going to be 5.5 plus 6.4, and we're going to get 11.9. The actual way to calculate this is using a technique called Moore's circle. It's a graphical technique for solving for the equivalent stress state of a given load case. So if we draw what the very top of this beam looks like, we get a normal stress of 6.4, and we get a shear stress of, you can never remember which way the arrows go, of 5.5. I don't know if that's right, but it doesn't matter. The circle is going to work regardless. We also have a normal stress of 0 in this direction, which is important because that's the first point we're going to graph is 0, negative 5.5. Then we're also going to graph 6.4, 5.5. And the circle that contains those 2 points is going to give us our equivalent stress state. So we get our principal stress and then our other principal stress here. The formulation to calculate that is going to be the kind of hypotenuse of this plus this point. Doesn't really matter. 5.5 squared plus 6.4 squared. The square root of that plus 3.2. 3.2 plus the square root of 5.5 squared plus 6.4 squared. So we get an actual stress of 11.63, right? So that is our real sigma prime. If we compare that to our estimated sigma prime of 11.9, we see they're very close. I like this method because it's very easy. It is a little conservative, so you'll always find a higher equivalent stress than you will analytically, but it's wicked fast and easy. Cool. So if we compare our 11.9 to the 40 we need to fail, we get a factor of safety of 3.36, which is great. So our inner tube is validated. Bang. We're now going to move to talk about our outer box. So the outer box, much like the inner tube, undergoes this much force, in a very similar loading to the tube. So we're going to have the 3600 of torque and the 150 pounds of load at a distance of 24 inches. So we're going to calculate the bending moment again, which is going to be 24 times 150. And we get 3,600. So we get 3,600 in both directions. We are now going to look at the cross section. And we see something interesting. This is an asymmetric cross section. So we're going to need to do a little bit more work on on-shape to figure this out. So our bending moment, our resistance to bending is going to be, I think it's going to be 1.67. Yeah, right?
3.7, but yeah.
Yeah.
Slipped out.
So our resistance to bending is going to be 1.637, and our polar resistance is going to be 3.808. So that's going to be our I, and that's going to be our J if we can look back at the paper.
Oh, yeah.
We also had our centroid be off axis. The point of maximum load is going to be whatever point is furthest away from our centroid, which not in my drawing, but in real life is this corner right here. So it's going to experience the maximum stress from torsion and also the maximum stress from bending. Cool. So back to MC over I and TC over J. So for MC over I, we are plugging in 3,600 times our distance from center, which is approximately 2 inches, divided by our bending moment of inertia, which is 1.637. We get 3,600 times 2 divided by 1.637. 4.3 KSI. We're then going to take our TC over J, so that's 3,600 divided by, what's that? That's root 5. Sorry, I'm just calculating the center rotationally, which is going to be 2.25. Divided by J, which is 3.8. meaning we get a stress of 2.1 KSI from shear. We're going to use the adding them together trick, which is a better name out there. And we get an equivalent stress state of 6.3 KSI, which if we calculate for aluminum, 40 divided by 6.3, we get a safety factor of 6.34, which is great. So box tube, that is. Now the last elements we're going to look at are the hook and the nubbin, I think we're calling it. We can look at the CAD real quick.
I'm gonna stop it there. Battery's about to die.
Great. These hook and nub onto the tower here. So as this rotates, this locks in and prevents rotation off the tower, and then this bolt and the nub allow the robot to torque against the tower. So those are the load cases there. So let's get to analyzing. The first thing we want to do is establish how big the forces on the nub and hook are as we try to resist our 3,600 pound load. Right? So we have one nub here, and the bolt that touches the tower of our hook there. Those have a center distance of, so it's going to be 2.47. Is going to be the reaction distance between the forces on our structure. If we take our 3,600 inch-pound force and, right, the units are inch pounds, so if we divide out the 2.47 inches, we're left with the reaction force in pounds. We get 1,457 pound force. So that's a linear force on our nubbin and our hook. So first we're going to analyze the nubbin. We're going to a side view. If we look back to the CAD, we're actually going to do our math with two assumptions. Always know the assumptions you're working with. If you disagree, you should do your math with different assumptions. We are removing our outer sleeve here because that is non-determinate and kind of shares the load with our bolt, which is a conservative assumption because the outer sleeve makes the bolt much stronger. So we're just doing our analysis on these bolts. Additionally, we're making a non-conservative assumption, which is that our force is applied about 2/3 of the way up our bolt here. Because as we load, and we verified this with finite element deflection, the bolt deflects away from the pole and our load shifts towards the root. It actually shifts like all the way toward the root, where it's like at the start of this fillet here. But you know, we're making the assumption that's going to be half an inch up. This bolt will bend if you load it with 1,500 pounds from the very end, but that's not what's happening. So this is going to be a side view of our nub here, 0.5 inches up. With we're going to round this to 1,500, which is, we keep saying conservative. Conservative just means that we're making it worse than it really is, right? A non-conservative assumption is one that's like, it's kind of idealizing your case to make it better than it is. But rounding up from 1,457 to 1,500 makes the math easier, and it increases our force. So we're going to analyze two parts of this. The bolt is in the meat of our plate, and we're pushing against it, so we're going to get a shear force, which for our 1/2 inch stud, we're going to find the area of that real quick. That's going to be 0.5. Wow, just no. It is pi r squared, so it's going to be pi times 0.25 squared, giving us an area of 0.196 square inches. If we take our force and divide it by that area, 1,500 divided by that is 7.6 KSI. Then we're going to calculate our bending force. So we're going to get our moment is going to be 1,500 times 0.5 inches equals, maybe I should feel confident doing that in my head, 750 inch-pounds of torque. So we are going to use a formula to find the resistance to bending of this stud. That formula is going to be 0.049 times the diameter to the fourth is going to give us our I value for this circle. So 0.049 times 0.5 to the power of 4 gives us 0.0031 as our I. That's going to be in inches to the fourth as our unit there. I'm not really sure what that means, but that's what it's in. So we have our M, we have our I, our C is going to be half the diameter of the bolt because we're analyzing this point on the edge here, or maybe this point on the edge here where it's getting pulled away like that. All right, so it's going to be 750 times C, which is 0.25, divided by I, which is 0.0031 equals, it's going to be a big number, 750 times 0.25 divided by 0.003. Whoa, 62 KSI. That is toe curling. My goodness. Look at that right there. That's a lot of stress. So with our 80 KSI number from before that we're using for steel, 80 divided by 62 is 1.3 exclamation point. Not not factorial, but just 1.3. That's a lot. That's a bad safety margin. That's not validated. Let's check that 80 KSI number real quick. So this is something that you can do for anything that you buy from a reputable parts vendor. So this is part 91259A722. It's a McMaster car shoulder bolt. So we can go in and we can check the actual equivalent stress that results in yielding. So we're going to type that number in the search bar. And we pull up a list of parts, then we can check the product detail, and we're going to get 140 KSI. How reasonable. How lovely from McMaster. That is very strong for steel. Mild steel usually does end up in the 80 KSI range. So maybe it's a different formulation. It might be stainless. What do they say? Black oxide.
Alloy steel.
Alloy steel.
It's an alloy.
It's an alloy, as opposed to all the other steel out here. So who knows? I guess it's an industry secret. They give a hardness. So if we really wanted to investigate the properties, we could figure that out. Okay. Back to the math. So we're going to take our 7.6 KSI in shear and 62 here and add those together, and we're going to get 69.6 KSI as our equivalent shear state, right? Is that a K? I don't know what I'm doing. KIS? KSI. As we compare that to our 140 number, we get 140 divided by 69.2.01. Ooh, validated. So that's really close. The only reason I'm pretty comfortable with that is we made a very conservative assumption, which is not considering the sleeve around our bolt at all. A lot of this stress is driven by our really low I. So the fact that I is 0.003 is like really, I mean, it multiplies your force by like 300 times as compared to an I of 1. So our outer diameter on the sleeve is 0.75. So if we instead did our math with 0.049 times 0.75 to the fourth, we get an I of 0.01. 0.015, and then plugging that back in, 750 times 0.25 divided by 0.015, we get 12.5 KSI. So this is what would be called a bounding analysis. So this is the non-conservative load case assumption. So the reality is that we're likely somewhere in between 12.5 and 69.6, depending on how load is shared, which is going from a safety factor of 2 to a safety factor of like 8 or whatever, because this is actually like 18. Okay, so this is like what engineering kind of gets down to is the trading off of these equations and knowing how to make assumptions and how those assumptions impact your calculations. All right, but overall, the nubbin is validated. Now time for the hook. Let's talk hook. So this is really the hook geometry. Sorry, the hook geometry that we're analyzing. We have these two bolts resisting the bending moment on the hook here, and also these two bolts resisting the shear. Should both bolts be resisting the shear? What do you think?
Usually, you can assume that for 2 bolts, as long as the shear is not like directly parallel to them, which it's not. So like you'd assume that the aluminum hooky john shifts such that both of them are taking some of the shear. Although I assume you would be able to do equal depending on where the shear is applied.
Yeah. So we'll take the conservative case and do shear on this one, and then that they're both resisting the moment. That strikes me as most true. Again, that's an assumption that comes from a few years of engineering, watching a lot of stuff break and doing some tests that you will build as you do more structures. Cool. So we're also going to assume the same behavior of this coming towards the root as before.
Back to pink.
All right. Now let's draw that out. So we have stud number 1, stud number 2, hook. We have one load that's counteracting this bending, the bending away from the pole. And then we have our shear load coming in here. All right. We're going to make the assumption that this area is resisting our shear and that this structure is resisting our bending. Let's do shear first because it's easier. So we're gonna have the same lateral force as we had before, which is 1,500 pounds. We're gonna assume the same 0.5 inch offset, which is not important for shear, but will be important for bending later. So we get 1,500 divided by the area we found before, which was 0.196, which gives us 7.6 KSI. Bang. So we can hold the shear load. We're good to go. Now we're going to calculate the torsion load. We're going to make the same half-inch assumption, 0.5, from the root there. This entire structure, if we look at it, if we look at the cross-section of these 2 bolts here, we would see 2 circles separated by a distance of... Who's to say?
0.8.
Is that a Mindus? Is that the center?
It's the center, yeah.
Okay. 0.8 inches. We're then going 0.25 inches to the edge, and then we're assuming that the load is an additional half inch off of that. 0.5. The bending center of this structure is going to be this line here. So if we want to find the torque applied from this vertical force on the hook, we're going to need to find its distance from the bending center, which is going to be 0.4 plus 0.25 plus 0.5, which is going to be 0.6 inches. Okay. Now let's find the magnitude of that force. So that force is resisting our entire robot wrenching force, which is, if we draw a side view of our robot on the tower here, 150 pounds on a
19-inch.
19-inch lever arm.
We said 24 earlier. That was a little
I
wrong,
see.
but it's all right.
A little wrong, but conservative.
Conservative,
right?
actually.
Because we are overestimating the bending force. So our box was even safer than what we first thought. So 150 times 19. That's going to be 2850. Is going to be our bending moment that needs to be resisted by our finger connection up here. So and this is going to be a side view of the faceplate and the hook. I don't know if you can quite see that, but we are pushing on the bottom and pulling on the top to resist our bending of the robot. If we can get a dimension there.
Just the height between the two, the push and pull. I guess it depends how far over the finger.
So
We'll go bottom of the finger to the center of that. Okay, I can do that.
But to the
intersection there.
Yeah.
No fusion.
No. To the very very bottom of our structure here. You know what I'm saying?
Yes. Okay.
Yeah.
Sorry.
So we're actually pushing through the faceplate down here, not through our other bolt. So our reaction couple distance is going to be the bottom here to the tip of the hook there.
Up to we'll go there. 4 to be conservative.
Yeah. So we're going to take that to be 4 inches. Okay. So we have a moment of 2,800 inch-pounds. So 2,850 divided by 4 gives us a linear force of 712 pounds. So 712 pounds on a 0.6 lever arm. That just cannot be right. Hold up, yeah, that's not right. So I did 0.4 times 0.25 plus 0.5, which is wrong. Yeah, okay, so that's gonna be a 1.15 inch lever arm. So 712 times 1.15 gives us 819.375 inch-pounds of torque from this one, and then we're going to add that to the other one because both of them act to torque against the structure. So it's going to be that plus 1,500 times 0.5, which is 750. So we're actually getting kind of equal components of bending from bending away from it as resisting, which is going to add up. But since we're resisting bending across this entire structure, I think we're going to find we're having a much better eye. So those summed together is going to be 750. Okay, now we need to calculate the bending resistance from these two bolts being this far apart. So what we're going to do is we're going to calculate the bending resistance of one bolt, which using our formula of 0.049 times 0.5 to the fourth. We get 0.0031 inches to the fourth as our bending resistance for one. We're then going to use what's called the parallel axis theorem, which is it's just a way. I mean, if you haven't taken physics, I don't know, but it's a way of separating bodies and weighting their distance. So as these become further apart, kind of intuitively, you would think that they would kind of help each other resist bending more, and that's actually a squared relation. So our moment of inertia from this little guy is going to be a times r squared, with r being the distance apart, so it's going to be 0.8. And a being the area of the circle, which is going to be pi times 0.25 squared. So that times 0.8 squared we get an effective added bending resistance from separating that much of 0.125. And then it's actually AR squared plus your initial I. So because this also has its own bending resistance over here, it also resists bending on its own profile. That's a little confusing. We'll link some resources below if you want to look into calculating bending moments. You could also go into Onshape and make these two circles and select their faces if you didn't want to do this. But we're going to get 0.128 as the contribution from this lower lug here. That's not another zero. Those are both colored in shapes. And we're going to add that to our 3,000 from before, so we're going to get 0.13. Right. Conservative again, because it's actually 3.1, but we're just going to round that off low. Which is, as if we compare it to the resistance of just one to bending of 3 thousandths, the addition of the second bolt is huge for our bending resistance. So, back to MC over I. We are doing, the moment is 1570. C is, so we're going to want to get this furthest edge here. Because this is going to be our point of interest right here on this part of the cross section. So it's going to be 0.4 plus 0.25, which is going to be 0.65 divided by I, which is going to be 0.13 equals 7.8 KSI, which, as compared to our 140 KSI at failure, nothing. We're also going to consider our shear, right? This one bolt is experiencing shear as well. So we're going to go that plus, we get 15.4 KSI, which if we divide 140 divide 15.4, we get a factor of safety of 9. Bang. So our bolts are now validated. The last thing we're going to do, I apologize, there are a lot of pieces here. Last thing we're going to do for the hook, there's actually one thing after this, is to define the stress at this point here, right? This is made of aluminum. Aluminum is kind of like weak, mushy metal.
Fake metal.
It really is in a sense. So we're going to make sure that we're not yielding at this top point here. So that's going to be just a pretty straightforward MC over I calculation. Our cross section looks like this. Our cross section is going to be,
I can just measure it live, yeah.
yeah. So we're going to be looking at the cross section of our hook at our point of interest.
Quasi-rectangular.
Yeah.
We have 3/4, 0.75 by, oh man, Fusion's not going to like this.
We can take that 0.6 number if you want.
Use that one. This is going to be fine regardless.
Maybe.
Call it 1.
All right. So as we look to define our hook cross section, we're going to go 1 by 0.75. The formula for the bending moment of a square is going to be base times height cubed over 12.
It's 12, yeah.
Okay. So 1 times 0.75 to the third divided by 12 gives us a bending resistance of 0.035 inches to the fourth. All right, so that is resisting our 150 times 0.5, which is going to be, no, hold up, I'm wrong. That's going to be resisting our 712, because our 712 is the vertical portion here. So 0.5 times 712 gives us 356 inch-pounds of bending. Cooked. 356 inch-pounds of bending times our distance to our point of interest, which is going to be 3/8 or 0.375 divided by our bending moment of inertia, which is going to be 0.035. All right, let's see if we can do this right. 356 times 0.375 divided by 0.035. So we get 3.8 KSI, which is well within our limits. 40 divided by 3.8 is a factor of safety of 10. Bang. So our hook, very much so strong enough. Our nubbin, to be seen. Two is a little tight if we're considering kind of like accelerations and whatnot, but very conservative, not including that sleeve. Cool. This is bordering on overbuilt. You know, what do you say typical safety factor is we're targeting?
I feel like 3 is pretty safe.
Yeah.
2 is a little. I mean, the only thing that was under 2 is our chain, and that's what snaps first. So it's hard to say what our other stuff is going to snap.
It would have been great to push this to failure, which we may. But
we might do right after our Michigan little event.
That'd be fun. But this 10 is a kind of an absurd number. That's like something else in your chain of strength should fail before. But it's costing us like a few ounces. Because all these pieces are pretty small at the end here, and gives you a lot of safety of mind, because this does retain your whole robot on the tower. So this hook failing would be mission critical. Bang.
Bang.
All right. You want to talk pins? Let's do a high level review of what we've kind of gone through so far. Yeah. All right. So I appreciate you sticking with us. We've gone through many elements of the design so far. We've done the pole, the box, the hook, the little prawn, the entire superstructure. And this is how you kind of become confident in design, is going piece by piece, following what's called the load path from high load all the way through no load, which is like at these final attachment points. It's like 10 pounds. And that gives you faith in every part of this chain. So the last thing we're going to look at is what is linking these validated components together. So if we look back at the pole, we have kind of two primary linking components that are under super high loads. The gussets and stuff back on the frame are like under some load, but those can be done by area or what have you. We have these two shoulder bolts, which are acting as pins that attach this pole to this box. The reason we use shoulder bolts instead of like packing this gap is it's called design for analysis. Pins are much easier to analyze than a packed joint or even welds, really, and enable you to be very confident in your math. So we use pins here that we're going to go into the math of, and then we're not going to go into the math of these brackets. So we did very rough bounding calculations on the kind of cross-sectional area of these screws, and their ability to resist the torsion and pull out here, in particular using the bearing strength of the aluminum. So if you... We go to that real quick. All right. So very simply, you have a hunk of metal, you put a bolt in it, you apply a load to that bolt. The projected area of that bolt, right? So this shaded area right here has to be able to hold the load of that bolt. In particular, when using steel hardware and something weaker, you can get kind of an ovalization failure of your bolt, which I'm sure you've seen before, when you're pulling too hard and the material can't resist you. So the area of that cross section is the diameter of your bolt and the thickness of your material. And that's it. So if we do our force divided by area thing again, let's say we want, let's calculate the critical force for a 1/2 inch diameter fastener. So D is going to be 0.5, the thickness, let's call it 1/8 inch wall, so 0.125. We have force over area equals sigma. Our bearing stress failure is going to be 50,000 psi. So 50,000 psi equals our our diameter of 0.5 times 0.125, 0.0625 divided by our force. Then we can multiply out the 0.0625, so 50,000 times 0.625, 0.0625. Yeah. So always like vibe check your calculations, right? Gives us a tear out force of 3,125. And you're not supposed to use commas because they're confusing, but so that gives us tear out force for a 1/2 inch fastener and 1/8 inch wall tube. So we did this math on, if we can look at the CAD again.
Yeah, to be clear, this is bearing failure, so like ovalization.
Yeah.
Tear out, you can do shear in the walls that would tear out.
My apologies. They are slightly different in kind of a subtle way. But tear out should be using the kind of side profile length. We're not going to get into that. But that's why you shouldn't put holes close to edges, because you really become at risk. You're losing material.
Of literally tearing out.
Yeah. Ovalization is when you just crush the walls around your fastener. So we did those calcs on all these hardware and found them to be super good enough.
Well, we did have to upsize them. We baseline 1032 bolts because that's what we use on most of our robot, and it's like almost always strong enough. But upsized to 1/4-20.
Yeah, justifiably, which was a first for me. Yeah, so these all stay strong. The right angle brackets are really kind of a little difficult to do analytically. So we're going to rip them in FEA. When things are weird shapes and kind of not long or beam-like, it becomes tough to analyze them because you get weird combined loads. I don't know if you have more to...
Yeah, I mean, FEA is finite element analysis, and it's like breaking this down into like a mesh of a bunch of little points, and then the computer can solve it for you. But yeah, definitely almost always possible to bound even a complicated shape with like hand calc analysis on both sides, which is what Jonah's doing now.
Yeah, so we could, but we're not. Okay, let's solve these pins and get out of here. All right, so we have our pole, we have our box. Both have been validated. They are connected with 2 pins. Those pins need to be able to transfer the moment between them. We can use the maximum moment in our pole to do that. The maximum moment in our pole is, I don't know, 150 times that length, which is, we called it 9 inches. I think we called it 9 inches.
Yeah.
9 inches. So 150 times 9 is 1350 of bending. So this force couple needs to resist 1,350 pounds of inch-pounds of bending. Those are how far apart?
Checking right now.
All right.
Getting a little center to center here.
I'm a little nauseated by his CAD navigation. Okay.
1.625.
1.625. So that's going to be 1350 divided by 1.625. That's going to be 830 linear pounds in each of the layers that we drew. We must consider, if we look at the side view, that each pin has 2 what we would call shear planes, right? Or 2 points where they're supported. So looking at just a pin here, they are supported here, and then loaded here and loaded here, right?
2-inch tube, 3-inch box.
Yeah. So that's going to be 3 inches apart, and this is going to be 2 inches apart. So this is the reaction from this right here. We also need to consider our 3,600 inch-pound torsional force, which divided by this 2-inch distance. We're gonna draw. I really do apologize for the number of pictures I have to draw. Each is slowly getting worse. This is 2 inches. So we get 3,600 divided by 2 is going to be 1,800 pounds. of linear force. So, third view, isometric.
Oh,
We have 2 pins. Ooh, isometric circle.
it's beautiful.
Beautiful. We have an inner tube. We have an outer box. The outer box is going to be represented by this line. When you see a line and then a lot of lines coming off it, it means it's fixed or it's just like a rigid thing. We're not going to care about it. So our torsion load is shared across all 4 of these. Right. So we have 1,800 pounds in each direction. Maybe be like, is that not doubling? But because they're on this 1-inch center, that's actually correct. So it's going to be 1,800 inch-pounds here and 1,800 inch-pounds there. Together is 3,600. But then those 1,800 pound forces are going to be distributed across our 2 connections here. So we're going to break that down into 2 900 pound components. All right. So now we get into combined loading. So we had 830 that's distributed across the 2 connections here. So that's really 415. And then we had 1,800 divided by these 2 connections. So all of the connections on this side have 900 pounds going vertically. All the connections on this side have 900 pounds going down. Then we add on, we switch to blue, which might be distinct, it probably won't be. We're going to add on the bending one here. So that's going to be 430 additional there, and 430 additional there. Then we're going to add the other way here and the other way here. This gives us a maximum bearing load of 415, I like that pen, plus 900. So we get a maximum linear bearing load of 1315 linear pounds of force. Now, that is distributed on an 1/8 inch of material, and our material is an 1/8 inch thick, and our bolts are 375. So 0.375 times 0.125. And then we're going to divide 1315 by that. And we get 28 KSI. It's a little tight on our tolerances. So we're going to take a bearing failure at 50 KSI. And we get a ovalization margin of 1.78. It's a little close. So I would maybe recommend going to 1/4 inch wall tube or 3/16 wall tube, right? Yeah, that's uncomfortable.
Or bigger pins.
Yeah, or bigger pins. Or farther apart pins. There are a lot of things you can do to mitigate this. That's a little high. We did kind of just rip that. We didn't see an ovalization, but it is above 1. But you're liable to like accelerations and bumping and jostling and bad machining. That's what factor of safety gives you. It gives you margin to the real world forces that are going on. All right. The very last thing to look at is the bending in this pin here. So we're going to take our 1315 number, and we're going to compare that to the ability of a 3/8 pin to resist bending in this direction over like 3/8 of an inch. So 1315 times 0.375, 493 inch-pounds of bending. MC over I. So that's going to be 3/16. 493 over I, 0.049 times 375 to the 4th. Gives us 0.000096. 493 times 3 times 0.7 75 divided by answer gives us 95 KSI. That's a lot of force. Hold up. Let me think a little harder here. We hadn't planned for another sheet. So it is the outer box tubing, the inner circle.
Yep.
This load is 1,315. That is resisted on this bolt here.
Yep.
This counteracting load is not. There's where we are. So that should not be the number we're using. It should be whatever that is for outer circle, which is still going to be 415, but instead of divided by 2, we're going to divide 1,800 by 3. We're going to get 600. So we should be using 1,015. Sorry if that's a little unclear. Because our box tube is bigger, the torsional forces are less. So it's going to be that times 0.375, which is still going to be pretty high. So we're going to get 380 times 3/16 divided by 0.9 times divided by 0.00096 equals 74. That's our bending. If we also consider our shear, we're still kind of getting up there. So that's going to be pi times 3/16. So pi times 0.1875 squared. 1315 divided by. So that's going to be an additional 11.9 KSI in shear. So if we add those together, we get 8.85 KSI, which is a bad margin.
We're still at 140 for the shoulder bolts.
Yeah. So 1.64. Yeah. So you should upsize those shoulder bolts to 1/2 inch. 1.64. Safe to fly, but not safe for a robot. So that's because in aerospace, typically the upper limit for your safety factor is 1.4. But that's if you really know all the forces and your analysis is much more robust than ours. I don't know if you can speak more on that or.
Yeah.
Yeah.
Pretty much.
Pretty much. So we're gonna get that actually not validated. It should be improved. All right.
Go ahead.
All right. So 1.7 not great. We don't actually do our hand calcs by hand. We did this to demonstrate what it would be like to do them by hand. We use a spreadsheet to do our hand calculations. That enables you to update your variables very quickly. So we thought we were very, very groovy at 5.8 and 3.0 for our safety factor on those 2 pins. That comes from one analytic error, which is that the couple distance it's not 2 inches times 4, it's 1 inch from the center times 4, which takes us down to 2.0 for our bearing stress failure.
And the only other difference is that we're using 56 instead of 50.
Yeah, so 56. If you look up bearing stress of aluminum, 661 T6, you're gonna get 56,000 psi. Yeah.
Nice part about the spreadsheet, exactly as Jonas said, is you can just update stuff. So, for example, if our robot weighs 300 pounds instead, bang, a bunch of safety factors are red. Pan over there, and you can just update stuff like that live, and it's almost not that much. I mean, it takes almost the same amount of time to type it in your graphing calculator, especially if you plan to redo it more than once.
Yeah.
So if you're what they call like sizing something, like for one of these bolts, then guess and check from a graphing calculator is an absolute pain compared to guess and check in a spreadsheet. You can even have Excel like guess and check for you using a function called goal seek.
Like if we go back to this hook calculation, had I made a based on assumption error in like the distance between these, I would have to redo all of this math in the same time frame it took me to do it the first time. So napkin math to bound your problem, great on paper, but kind of as soon as you're doing more than that, I'd recommend moving to a computational solution.
Not all groovy.
We were pretty groovy. We're not entirely groovy. We hope you learned something. I think this is gonna be pretty long, but we had a good time making it. Remember that bending makes forces crazy. Torsion's usually more chill. Normal's always okay. Do your math. We look forward to seeing you flip climb if you do. Let us know if you have any questions or need any follow up.
Yeah.
Yeah. It's our pleasure.
Bang.
Bang.